All right. Hello, wonderful people. Let's see what we're doing today. Today, we're going to classify polynomials and identify key characteristics of polynomials. And we'll also identify the end behavior of various degree polynomial functions. All right, so what you need to know about polynomial functions. Polynomial function, they follow this form, and it looks confusing. I know there's a lot of stuff going on in here, but let's kind of take a page from a previous lesson, and I'm going to circle each term, and it'll probably be less confusing when you start to make sense out of it. So I'm going to go ahead and circle each term, which in this case, it looks like we have 6 terms. Now this break in the middle is basically saying that this could be for any number of terms. So for this example, I'm going to say 5th power. Let's just use our imagination and pretend that this highest degree, or the highest exponent, would make this a 5th degree polynomial. So 5th degree polynomial would mean that this is going to be the first term, what we call the leading coefficient. So remember, coefficient is the number in front of the variable, and the leading coefficient, in this case here, is our first number. And this is assuming that it is in standard form, which this is like standard form. It has to go down in terms of power of each term. So what this means is a times x to, and again, I'm going to use the example of 5 power. Let's say that this is a 5 power polynomial. Going down, the next term down will be that number minus 1. So the 5th coefficient, you take the 5th one, minus 1, and that will be the 4th number. So n minus 1 simply means go down 1 power. So this would be the 4th term and the 4th powered polynomial. Go down again, since we were working with 5, 5 minus 2 is 3. So our 3rd coefficient is this number here. And this would be 5 minus 2, which is 3 power. And again, this means it can go on for any number of terms. So we could have a 10 power, we could have a 15 power, which I don't think it's going to be that high for any of the exercises. And here we have the second to last, so the 2 power term, the 1 power term, and then our constant value that has no power term. So even though it looks confusing, it's just basically saying that it's in descending order of powers. And all these coefficients are real numbers. So in other words, you should have real numbers. So that means it's okay to have fractions, it's okay to have negative numbers, but you cannot have things like imaginary numbers or undefined numbers. A to the n, and again, that's your highest power, the leading coefficient, cannot be equal to 0. Now I'll kind of explain this in a second here, hopefully. N would also have to be a positive integer, which means that you cannot have negative exponents. So again, it feels like a lot of information, but basically you can't have negatives. They must be arranged in descending order, and your first term cannot have a coefficient of 0. So let's talk about classifying these polynomials by degrees. And we're also going to give the leading coefficient. So on this first one here, I have the example of 4. Y equals 4, or f of x equals 4. Okay, so if it is, what is the degree? So the degree is the highest exponent. Well, in this case here, we have x of 0. So our highest degree is 0 degree, which 0 is the degree. And if we take the highest power from in this case, x of 0, the number that is paired with it, the coefficient for that is going to be 4. The leading coefficient is 4. So even though this has no power, it is still considered a binomial with a leading coefficient of 4. All right, let's go ahead and move on to the next one here. So I have negative 5x plus 1. So I have a binomial with 2 terms. And if I look for the power, I have x to the 1 power, which is just going to be, well, 1 power. Since that's the highest degree, that is the degree of the polynomial. And our leading coefficient shall include any sign, whether it is negative or positive. So in this case, we take the negative with it. So negative 5x is included in this one here. Now let's go ahead and get to the third one. In this case, we have a trinomial. So this trinomial here has the highest power is 2. So 2 power, 1 power, 0 power. So that makes this a 2-degree polynomial. And the power, the highest power 2 is paired with the coefficient of 12. So that would make this leading coefficient 12. Now, I think this is pretty easy because they're already in descending order, right? It's already the standard form for a polynomial. It should go down in power. So to find the highest power, we simply go to the first number in the sequence, which in this case is 3. But double check it, you never know. Sometimes they might be out of order. 3, 2, 1, 0 power. So in this case here, that is going to be a 3-degree polynomial. All right, so go to that 3-degree, look at the coefficient, the number in front of our x value. And in this case, it's going to be negative 1. Don't forget, anytime you have or you don't see a coefficient, the coefficient is 1. So it's negative 1. Also, don't forget that these negatives go with the number. So in that case, it would be negative 1. So let's go ahead and do this one here. So now we're skipping some. We have a trinomial, but it's a 4 power. So we're actually missing one of the terms. Well, we don't really need it actually. Just look for the highest power, and that is your degree. So in this case, it's a 4-degree trinomial. And the leading coefficient is negative 3. All right, so here we have a 5-term polynomial, which is actually what we would call it. We'd call it a 5-term polynomial. The highest power is 5, so that would make this a 5th-degree polynomial. And again, it's not degree as in angles or temperature. It's degree as in grade, like a degree, like the kind of education level you have. And the leading coefficient for this one will be 9. And there we go. Those are all the those are the 2 ways that we are classifying polynomials, by degree and leading coefficient. Alrighty, I'm going to go ahead and move on to the next point. And that is talking about the parent functions of these polynomials, so the parent graph. So identify each parent function, then sketch a graph using your graphing calculator. So for this one here, we are not going to use our typical graphing calculator. So this is what we would use if we were in, say, in-person classes. I don't think a lot of students would have these, and actually they're a little bit tough to use, so we're not going to use them. Instead, I'm going to show you another better tool. So go ahead and copy this down. If you don't get all of it, don't worry too much about it, because we are going to come back to this slide pretty soon. So go ahead and just try to get as much of these as you can. You probably won't get all of them. That's fine. We're going to go over them one by one anyway. So we have a constant graph. Now, if you're following along in your worksheet, you will notice that this actually has only these 4 on the same page. The rest of them are all on these 2 are on a different page. So f of x equals c. So our first type of function is the constant function. So a constant, just as the name kind of means that it is not going to change. All right, I'm going to go ahead and move over to the slide in 3, 2, 1. So there we go, moving on over to what we need to work with. And this is my messing around slide, so I'm going to go ahead and use this one here. So I'm going to change f of x to y, because don't forget f of x and y basically mean the same thing. And I'm going to come up with a number. I'm just going to pick a random number. I'll say 5. Okay, so there's our function y equals 5, and 5 is constant. So remember that x can change the meaning. I can say x of, say, -5. If I put the input x of -5, my output will be y is +5. If I move over to, let's say, -1, my output is still 5. My y value is still 5. If I move over to 6, my output is still 5. It's constant. It doesn't change. That's why we call these constant graphs. So let's go ahead and I'm going to go back to the worksheet, and we are going to graph this line. Now, again, the parent function should really be down here, but I'm going to stick with 5 just because you can see it a little bit better. So we have a horizontal line that does not change either direction. All right, so let's go ahead and move on to the next one. The next one is the linear function. This one should be a very easy one. In fact, you might even know this one without covering any sort of refresher, right? So if I had to graph y equals x, well, there's no slope. Well, I should say there is a slope of 1, which means up 1 over 1, up 1 over 1. And if there is no b value, that means the y-intercept is 0. So we should be able to graph that one, no problem. But let's go ahead and go back to the graph really quick, and I'm going to go ahead and talk about that, because I did mention that I was going to talk about parent functions. So I'm going to go ahead and graph, why the leading coefficient cannot be 0. So we talked about why the leading coefficient cannot be 0. So here I have my basic parabola. And I am going to, I'm going to make up a new parabola, okay? There you go, that's something like that, okay? So I just made up some numbers so that we have a parabola. But what happens if I make the leading coefficient 0? So I'm going to type 0 into this function so that our x squared is now 0. So keep an eye on it. Let's see if I can, here we go, in 3, 2, 1. We end up with a linear function. And if I put something back there, it goes back to being a parabola. So anytime you make something 0, the leading coefficient, that reduces the power of the entire function. So again, if I put 0 in here, it's basically going to turn into a line function. So that's why you can't have a leading term of 0, because now this is no longer a 2 power or a quadratic function. It is a linear function if you get rid of your leading coefficient. All right, but anyway, let's go ahead and graph our parent function for linears, and that is going to be y equals x. And like I said, goes through the origin, 0, 0, because there's no y-intercept, up 1 over 2, up 1 over 2, up 1 over 2. And while I'm here, I'm going to go ahead and go do the third one, so that is the cubic function. Now, there are 2 ways you can type this into Desmos. And I'm going to show you how to do Desmos because we have, well, that's the only thing you're really going to have, okay? So if you have internet, you have Desmos. So the first way is to type in this button here, so a squared, but unfortunately we need a 3 power, an exponent of 3. You can highlight your exponent and then type in 3. And that should give you a new exponent of 3. That's probably the easiest way, but you probably don't want to type it because we don't have, there's no button here that says 3 power. At least I don't think so. There may or may not be one. But either way, this one, we don't have 3 power. So let's go ahead and anyway, there's our function. And we should also know that our square, right? So if I square this, that should just be a parabola. So we've done a lot of parabolas in the past. In fact, the entire last chapter, most of November, we were just working on parabolas. Okay. So let's go ahead and go back to our worksheet and fill those in. So the quadratic, again, no big surprise. Just do our best to draw a parabola. So it's a little bit parabolic shaped like that. And the cubic one, so hopefully you remember that one. But if we look at the cubic, I'm gonna go back to the graph really quick. And I'm gonna replace the 2 with a 3, oops. Now there's also a second way you can type in a power, so that is to hold the shift button, hold down shift and push 6. You have a weird symbol that kind of looks like an up pointed arrow. And that will allow you to type an exponent. And this works with all types of computing programs. So not just with Desmos, but it really works with everything. Like Microsoft Excel would be an example. You can type in exponents using the Shift 6 button. So there we go. We have x, or in this case, y equals x to the 3rd power. And you notice that we have this weird kind of line. Now, okay, so what you need is the parent function, but I added an extra x in there just to show you what happens. And you get this n looking thing. It kind of looks like the letter N where it goes up, down, up. But this is the one you need to look at right now. This is the one you need to graph. So let's go ahead and get back to our worksheet and graph it as is. But I'm just trying to show you that there's a little bit more, going on. Than you might think. And I'm trying to introduce a little bit at a time, even though I know it's can be a little, overwhelming to have a lot of information thrown at you. And this is also going to be a little bit thinner. So it might look like a parabola with one side turned down, but actually it's a little bit thinner. Okay. So it's a little, if you, again, so take the parabola and turn one side down, that might be what you're thinking of. But in this case, it's not really what we need. So I'm going to go ahead and we're going to graph the 4 power function in just a second. So let's go ahead and go back to here. But like I said, if you want to make it look a little bit more 4 power function like, you can add an extra variable in there and that will cause it to be a little bit more, there are going to be more turning points and stuff like that in there. And I'm going to compare it to a quadratic function. So again, our parabola is blue and our cube 3 power function is purple. So it is a little bit thinner. So looking at it from the bottom, it doesn't look like it's all that different, but I just wanted to point that out, that it's a little bit thinner than a parabola. So there we go. I punched in 4, so this is our quartic function. Quartic is like quarter, meaning 4. So let's go ahead and get back to the worksheet and put this one in there. So it kind of looks like a parabola with a squished in, flattened nose, little flattened point. And this one's going to be a little bit of a tough one to draw because, again, it does kind of look like a parabola, but there's a little bit of a missing point in there. Kind of looks like that. Okay, it's not perfect. But hey, it'll probably work for what we need it to do. Hey, there we go. Not bad. All right, let's go on to the final type of graph, and that is the quintic function. So you don't really hear a lot of people say quintic. I mean, there are a lot of words in everyday English that use the word quart, or like a quart of milk, or like the other word you might see is for 4 is quad, like quad bikes, meaning 4 tires. But quintic, you just never see it. It's just never around. I don't know of any words that would have the word quin in them, except for like quintuple. But let's go ahead and graph this last one, the 5 power function. So I'm gonna go ahead and go back here, and I'm going to punch in the 5 power, and it kind of looks like the 4 power one with something one side turned down. The one side is turned down. Okay, so let's go ahead and get back to our function and, worksheet, and graph that function. So let's go ahead and do that. And again, I'm going to go ahead and put a little flat piece in here. I'm going to put it a little bit above the line just so it's a little bit more visible on my graph. And I'm exaggerating it a little bit. There we go. So these are the parent functions. And again, parent function means the most basic form of that function. All right, so I think we're done with this. Let's go ahead and move on to the next type of exercise. And that's going to be end behavior patterns. So right here, I already have them put in, right? They're already, the answers are there. I'll give you a few seconds to copy them down, okay? So take this moment, copy them down, because I'm gonna leave this page and I'm gonna stay with the graphing for a while. Okay, I'm gonna stay with the graph for a while. And that way you can follow along while we're doing the exercise. And it's just infinity and negative infinity, but make sure you get the right sign on there too, because some are going to be positive infinity and some are going to be negative infinity. All right, you got them? We'll come back to this in a little bit, but like I said, I'm going to be over in the graphs, and I'm going to stay there for a while. So get ready to go, and we will switch over now. So here we go. For number 1, I already have it graphed. And we get this weird shape with our, and you'll notice that this is a little bit different than the parent function, because when you start adding in extra terms, you start getting, well, extra what I call segments in the graph, in the function. So right now we are concerned with only the end behavior. What is the function doing at the far right and as we go all the way to the left? So end behavior means we're ignoring everything in between. What is the last thing that it does? So the first thing that it asks us is, what happens when x goes to positive infinity? So as we go this way, right, to the right, as we move it to the right, what is the line doing? What is the function doing? That's the f of x part, or the y, which way is the y going? And here we can see that the y is going up. So as we move to the right, the line goes up. Now it's moving up very, very slowly, but yes, it is definitely moving forever up and to the right. And as we go backwards to the left, so starting from the last thing that it does, as we move to the left, that is towards negative infinity. The line moves upwards as we go to infinity. Again, it's going up pretty slowly, but it is still going towards positive infinity. All right, let's go ahead and move on to number 2. So for number 2, I have here my graph, so that is negative x squared plus x. So we have a parabola opening down. So if you remember, oops, there you go. In this case here, we have a leading coefficient that is negative. when you have a leading coefficient that is negative, that means, well, in parabola terms, that means your parabola is going to open downwards. All right, so we have a opening downwards. As it opens downwards, that means your left, well, we could call it the arm. The left arm and the right arm are both going down. So as I go towards the positive numbers, y is going down and down. As I go left towards x of negative infinity, the line is also going down. So that's why if you looked at the worksheet, it says that they are both going towards negative infinity. So down to negative infinity in both directions. They're both going down, right? As I go down here, it's going down to negative infinity. All right, now for this one here, it's going to be a bit of a different thing. So this is problem number 3. And it's a very simple cubic function. As far as cube functions go, this is a pretty simple one. Now again, looking at the end behavior, what is the last thing it does as we move to the right or towards positive infinity? So as we go towards positive infinity, it is going up. We are having an upward movement on the y-axis as we go to the right. As we go to the left, it is going down. So on the worksheet, it says as x approaches infinity, the function goes up. As x goes to negative infinity, the function goes down to negative infinity. All right, now I'm going to leave this one up because number 4 is a very similar problem. So for number 4, I'm going to go ahead and switch over to it really quick. So keep your eye on this graph. And I'm going to switch back and forth between them. And you notice that it kind of looks the same, but opposite, right? It's switching direction. They're both cube functions. Now that 2 does make a difference, but it's not a really big difference. But a lot of these functions will follow patterns on how they behave. So that's going to be a little bit important later. So let's go ahead and look at the end behavior of this one. So as we go to positive infinity or to the right, we are going downwards to negative infinity. As x goes positive infinity, y goes negative infinity. So negative infinity is the first one, and the second part of that answer will be as x goes to negative infinity. So as we go to the left. As we go to the left, we are going to positive infinity. There you go. And again, end behavior is the last thing that these graphs do. And I'm going to go ahead and move on to number 5. We have this function here, this parabola. And if you go to the home screen, you're only going to see the very top of it. So you got to kind of drag the window around until you can see all of the, well, you can see as much of the function as you want. That's one good thing about Desmos, whereas if you're using the hand calculators, moving the window is a real chore, and it takes a while too. So you got to kind of know where the graph is to go looking for it, because you have to kind of type in which way you're going to go, and it can only take you so much in any direction. So looking at this one, now it is a parabola again. It has a negative leading coefficient, which means it's going to be opening downwards. And as we go to the right or to the left, it's going down to negative infinity in both directions. So that's why we say as x goes to positive infinity, y goes to negative infinity. And as we go to negative infinity for x, so as we move to the left, our line is going down to negative infinity. So both sides are going to negative infinity. All right, last one. So 1/2 x to the third power plus 7. So we gotta look at our graph here. So looking at our graph, we can see that the function is going up. So that means that the first one is going to be going to positive infinity. And as we go to the left, as we go x to negative infinity, it is going down y negative infinity. Don't forget these lines go on and on forever, so that's why we say negative infinity. And there you go. That was actually a little bit better than my earlier classes. I had to sit here and type it in front of them as we were going through it. So I just sort of improved it a little bit to have the functions already ready for us, because all it is just typing it in. And Desmos, like I said, Desmos is pretty easy about the graph. And as you're looking at the last one here, so negative 1/2 x to the 3 plus 7. Again, as we move to the right, line goes up. As we move to the left, line goes down. So there we go. That is it for the end behavior. Actually, no, I'm sorry. We're not quite done with end behavior, because now I'm going to kind of point out. You'll kind of notice that some of these are negative. Some of them are positive. How does that impact what the function does as its end behavior? All right, let's go ahead and cover that in this next slide. So say goodbye to this one. All right, not a whole lot going on with this one. The only things you have to fill in are these lines that are kind of going a little up or a little down. Either direction you look at them. Okay, now let's go ahead and get this pattern down. So to help us remember it, we're going to sketch these lines here and talk about the leading coefficient. So if your leading coefficient is positive, what's that going to do to your line? So for this one here, this is like that first problem, number 1, where we had that W looking thing. So we had that W looking thing that comes down, up, down, and then up. But it came from the top and left to the top. So it came from positive infinity and ended going towards positive infinity. So there you go, that's that one. What if it was an odd degree? So think of a 3 degree, the 3 degree function, right? Remember how I kind of say it looks like an N? So it does kind of look like an N. And it has 3 segments. One goes up, one goes down, and a second one that goes up. So there are 2 ups and 1 down. And again, that's going to look kind of like this. And if you were to take a parabola and turn it negative, it goes from opening up, which is positive, to opening down, which is negative. An odd degree, if you have an N, so think about that one. Remember how I told you on question number 3, look closely, because when I switched it over to 4, it did a flip. It did a flip where it was switching the direction that it was going. So let's go ahead and look at these questions 7 and 8, and it says to determine the following, determine the sign of the leading coefficient and whether the function has an odd or an even degree. Okay, so is this odd or even? So let's see, leading coefficient. So let's see. First off, is it negative or positive? Now, I think for me, I would say the easier thing to do would be finding out whether it is an odd or an even. So if you think about an odd degree, like a line, it starts from one direction and goes to the other direction. Parabolas start from one direction and goes back the same direction. An N type thing, where it looks like the letter N, it ends in the opposite direction that it comes from. The 4 power one can look like an M or look like a W, well, backwards, I guess. In this case here, we have something that looks like an M. There are 4 segments, one that goes up and one that goes down, a second that goes up, and a second that goes down. So there are 4 segments in direction. That means this is a 4-degree polynomial, so that we can say that it is an even degree. Now, once we know that it is even, we need to find out whether it will be an odd, positive or negative leading coefficient. And that's where this chart helps us out. So we know it's an even degree, so it's got to be one of these. Does it come from the top and leave to the top? Or does it come from the bottom and leave from the bottom? In this case here, it comes from the bottom and leaves to the bottom. So it like opens downwards as a parabola. Number 8. So in this case here, this is the n-type function I was talking about earlier. Now we can tell this is a 3-degree because the 3-degree one is one that shows up a lot, the cubic function as it's called. This one again looks like an n or sometimes a backwards n. There are 3 segments. In this case, there are 2 that go up and 1 that goes down. So that's 3 directions that this thing turns. Or sorry, not turning, but there are 3 segments that have an up or a down. And that's actually going to come into our next lesson. And that is where, well, we call them turning points, but we'll get there when we get there. But I just want you to pay attention to how many different directions that these things go in. So anyway, we know that this is going to be odd degree. In fact, I know it's a 3-degree. And let's see, okay, looking at this, is it positive? So look at the direction that it goes. So as we go to the left, it goes down. Okay, so far so good. And as we go to the right, it should go up. So that means that this is an odd degree positive n behavior function, right? The polynomial has a leading coefficient that is positive, and it is an odd degree. In this case, it's 3 power. Okay, so again, I did kind of mention that a lot of these are, and I'm going to go back and I'm going to show you some of the graphs that we have done. So this is a 3-degree, and again, it kind of looks like an N. Here I have a, I erased some of them, but again, this is a 2 power, so it only has 2 directions, one up, one down. 3 power again. Now this one, it looks like it's going down, but there's a little bit of a change of direction there that you can barely see. And if you have a 5 power, again, it's going to end in the opposite direction that it's coming from. So that's our 5 power function. All right, so next thing we need to cover is basically what I was just talking about. The we call them turning points. Although, if you remember from quadratic functions, we called them vertexes or vertices. However, we have a new name for them. Vertexes is only what you call them when they are in a quadratic function. So in this case, we have turning points. And the number of turning points, in fact, you know what, this is important. Now, I said this to all of my morning classes and my 3rd hour, but I didn't type it down. I think typing it out would probably be a little bit more helpful because I think in most cases, people are more likely to write it and more likely to remember it. So the number of turning points is 1 fewer than the degree. So this is the exact function we were looking at in the last slide. And it has 1 turning point. So it goes up and then it turns down. The second turning point comes from going down and then it turns upwards. So this one has 2 turning points. However, it is a 3-degree polynomial, or a 3-power function. So it has 3 directions, but 2 turning points. Okay, you with me so far? And turning points, the name makes a lot of sense because it's where the polynomial switches direction. Now, when we were talking about parabolas, we were also talking about maximums and minimums. But in this case, we're talking about relative maximum. And I don't mean your cousin or your uncle or anything like that. Relative means compared to. So in this case, the turning point is higher than any nearby point. So we call it a relative maximum. And I'll explain that. So this is a maximum, but it is not the highest point in the graph. What is the highest point in the graph? Well, I mean, don't forget, this line goes on and on forever, right? It's going to keep going to the right and keep going up forever and ever and ever. Okay, so that's not the highest point, but compared to the area around it, that is the maximum. That is the maximum turning point, basically. And then in the same sort of thing, we have a relative minimum. So if you look at the area nearby, it's the lowest point. So that's why we call it a relative minimum, because it's not really the minimum. But when you compare it to the other area around it, it is pretty low. All right, maximum and minimum values are called the extrema. And this is what we used to call in quadratics the vertex. So here I have 2 extrema actually. I have a high extrema and a low extrema, but we just call them extrema, and that is the value of those points. And again, turning points are where it changes from increasing to decreasing, but it can also change from decreasing to increasing. Okay, so I hope that makes sense. And I know this is a lot to cover. Let's go ahead and keep things moving along. So for this next one, it's going to tell us to use a calculator. So again, I don't have a lot of these. We're not going to mail them out to students and let them borrow them. And it gives you the directions. So if you were using this type of calculator with, in person, you would type in I don't think this one even works, but you would go to graph and there would be a place where it says y equals, and you put your function in there, and then you push y equals, and then you hit graph, and then it'll give you a graph. But the resolution on these are very low, and it's really hard to find the minimums and maximums or turning points for these kind of calculators. But you're in luck, because if you have internet, if you're watching this, then that means by all chances you do have internet. We're going to use Desmos, and that's exactly where I'm going to go next. So let's go ahead and move over to Desmos, and I'm going to punch this equation into our graphing. So x shift 6 to the third, and again that allows me to put the x to the 3 in there, negative 6x square plus 7x plus 2. So I end up with this 3-power function, and again it looks like a letter n. If I were, and just remember what we were talking about with, I'm going to go back to n behavior really quick. Remember when we were talking about n behavior, I said that if you make it negative, it's going to flip direction. So you can see that it is flipping direction, and in fact the zeros are not changing. So that will cause it to flip direction. So I just wanted to point that out from n behavior. Now for this one here, we are looking for the turning points, and that's again pretty easy to do with Desmos. You don't have to go to control or menu and scroll down and pick all these numbers with the calculators that we have, like this one here. Instead, we are going to move our cursor over to the point that we want. In this case, we're looking for our extrema, in this case, relative maximum. And anytime I move over one of these gray dots, it shows me the number. But if I want to have it stay, I click it and then it turns black, and that will cause it to stay up. So now I can see that 0.709 and 4.303 is the maximum, the relative maximum for this number. And I'm going to go here, that's a 0. We don't need that right now. And I'm going to go ahead and punch in this number here. So make sure you get those numbers, okay? And you can go ahead and go back to your worksheet and punch them in, which I am going to do right now. And for me, I'm going to go ahead and round it down to 2 decimal places, because on some of these, I will run out of space if I do not use, I made the text a little bit smaller, but that doesn't help out a whole lot. So in this case here, I got my relative maximums and relative minimums. Now we have to pick the increasing intervals and the decreasing intervals. So we want to pick the x values where the line is going up. So where are the lines going up? Let's get back to our graph here. And we can see that there is an area here. So it comes from negative infinity. Don't forget this line comes from negative infinity. So all the way up, goes up, and we have a turning point. So I can mark out my turning points. Like, so we have one here at 0.7, and we have another one down here at, let's see, the x value is x equals 3.3. And you can see here between this black and green line, so it goes up, reaches here, and then it stops going up and then turns around. At this point, it becomes a decreasing interval, going down, 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 reaches its minimum, stops, turns around, and comes back up. So what we need to do is we just need the x values. So that is this number, the 0.7 number, and the 3.3 numbers. Now I'm going to get my vertical things out of here. I was just kind of showing you where it was going. So in this case here, it is, I'm going to round that off to 0.71. So the x value for the increasing interval, that is negative infinity. And I don't really like interval notation. I mean, there's very few things I really dislike about math. And one thing that I very much dislike is I really wish that they would have come up with a better system of interval notation, because it looks like an ordered pair. If without any background information, this looks like an ordered pair. If I just told somebody, well, okay, if there was negative infinity, I'm sure they could figure it out. But if there were regular numbers, no infinities in there, someone's going to say, well, that looks like an ordered pair. And it does. It does look like an ordered pair. All right, so now in this case here, we're looking at the decreasing interval, which there's only one, and that's like the low to the high as we go down. And that is going to be this number here. So between those two numbers, between x of 0.71 and 3.29, those are the intervals that it's going down. After that, it stops going down in either direction. So again, this is a fairly easy lesson, I guess. Most of it's just kind of plugging stuff in. And again, don't worry about all this information. These are for calculators that you are not going to use. I think Desmos is way better. Hopefully you remember how to get to Desmos. You just open up your internet browser, go to the search bar, address bar, whatever, type in DESMOS, and there you go. You got to your graphing utility. All right, so the last thing, moving on to the very last type of exercise. This is drawing a graph and identifying the key characteristics of our function. Now I went ahead and left them up there already. So they're already here. Don't worry about it. They are there. Okay. So go ahead and copy down the domain. I'm going to go ahead and get this ready to be graphed. So graphing this up. Okay, so I got this one graphed, so I'm going to go ahead and move on over here to the graphing screen. And here we have that N shape that you generally see with cubic functions. You got the little N shape. So the domain, this graph goes on forever in both directions. Now again, it's going up really, really fast. And even though it's only moving to the right a little bit, very, very slowly, it is still going to the right and to the left infinitely. So that's why our domain and range is all real numbers, all right? And if I have a value of, say, y equals -10, and I were to make a slider that goes up, my blue line is able to intersect my red line all the way down and all the way up. There is no holes or gaps anywhere in this line. So that's why our domain is all real numbers. We have a relative maximum at -2, 4. Oops, sorry, didn't mean to. If you double click, it zooms in. So, and we have a minimum at 0, 0. And behavior, okay, so again, we've already covered this, and we've also covered it in several other previous chapters. So as we go to the right, our line goes up. The line is going up. And as we go to the left, as we go back towards the negatives, negative infinity, our line is going down. We have one increasing interval until we get to -2. And then we have a decreasing interval from -2 to 0. And then after that, we have a third segment, which is increasing. So we have a second one that is increasing. So there will be 2 increasing intervals, and that is from 0 to positive infinity. And there we go. There's all the information. Now, graphing this is a little bit of a challenge, okay? I understand. Now, when you graph these, I want to focus on a few things. Let's focus on having our key features placed somewhere on the graph. So if you remember, there was one at 0, 0. And then we had another one at over 2 up 4. Oh, shoot. You know what? Did I make a mistake? I think I made a mistake. I think I bombed it big time. Yeah, this one was supposed to be negative. My bad. Luckily, that doesn't change a whole lot of things. Well, and again, you kind of notice because if it's negative, that means it's going to end going down. So luckily, I caught myself on that. Would have been bad if I did not catch myself on that. But again, knowing a few things about this can help you kind of spot mistakes before they happen. So I did my minimum and my maximum, because again, I have it already here. So over 2 up 4 is my maximum, 0, 0 is the minimum. And again, we're having an interval increase from 0, that's this here, to 2. And we have a decreasing interval, and those are the first 2 that I drew. Those are the ones that are going down. So those are my 2 values going down. Okay, so there we go. That is the first one. And I'm going to kind of go a little bit quicker through these next ones, because now hopefully you're a little bit, you kind of understand a little bit of what's coming on. So here we go, moving on to the next parts. And there's a lot of stuff going on with this one. So go ahead and follow along with this one. And I'm going to go ahead and get the graph ready, make sure I actually get all the stuff right this time. But that just goes to show that anyone can make mistakes. You know, you should never hate somebody for admitting their mistakes, but you should really hate people that fake perfection. Okay, so if you didn't get everything down, that's okay. We're going to go ahead and I'm going to move over to the graph now. We'll come back to this slide in just a bit. There we go. So hopefully you can see the graph now. So let's look at some of these key features now. In this case here, we have 2 minimums and 1 maximum. 2 minimums, 1 maximum. We can also see that the end behavior, as we go to the right, our line goes up. As we go to the left, our line also goes up. So as x, you know, in both directions, it's going to go to positive infinity, both directions. Our domain, now this one's a weird one because if you look at our domain, as I start from the bottom, so I'm going to start with my slider so you can see, like if I tried to get a y value of -4, it's just not going to happen. We are not going to get a y value of -4. The lowest y value that we can get is about there. Okay, now I can't adjust this so fine to where it's there, but we can click on our minimum and see that that is the lowest point. Our lowest y value is -3.31. So that's why the minimum is it's y values greater than or equal to -3.31. And we have 4 directions: down, up, down, up. So 2 ups, 2 downs. So there you go. You can see our graph here, and I'm going to go back to our work page, and I'm going to try my best to graph this. So, and I don't get it, you don't need to get it so precise. Okay, you don't need to have it like, you know, if you're off by a little bit, I'm not going to mark it wrong or anything like that. But I'm just trying to get the key features as close as I can. And this is always a bit of a tough thing to do. We end up having something that kind of looks like this. I'm gonna be a little bit different about that. That's probably not going to look exactly like that, just because of the way I'm drawing it. It kind of looks like it's flattening out on one side. If you look right there, it kind of looks like no. It's more of a more straight line. But otherwise, if I tried to draw it by hand, it would turn out all sorts of different ways. But again, you can see all of the things we need in this case. So again, we have our increasing intervals and our decreasing intervals. So the parts of the x value where it's going up or going down. All right, and that is it for number 2. Let's move on to number 3. So again, here are the features, and don't worry, I'll give you a couple of minutes, I'll give you about a few seconds to get that one copied down, and I'm gonna go get the the graph ready. That way you're not trying to write it while I am discussing it. Okay. And if you haven't got it all down, don't worry about it because we will come back to it in just a moment. let's move on to our graph. So in this case here, I have a weird looking M shape where one is way higher than the other. So, right, we have one maximum here, or actually let's go down the line in talking about all of the features. So again, sideways domain, it's all real numbers. As I go X in both directions, the line's going down, and it's going down really, really sharp, but it is still moving sideways infinitely. So domain is all real numbers. Y values, we do have a maximum. If I wanted a Y value of, say, 7, can't happen. 7 is not in the range. The highest number I can pick would be about this 6.5 number, which actually, I think it is actually 6.5. Oh, what do you know? The range is actually 6.5. So all Y values less than 6.5. Looking at the end behavior, again, it goes down in both directions. And the relative minimums and maximums. So I'm going to go move this back out of the way. Let's go ahead and click on our minimums and maximums. So I have two maximums, this one here and this one here. We also have a minimum here, and now we just have to use these points to show the interval of where the increase and decrease are, the areas that are increasing and decreasing. So I'm going to go ahead and mark out our turning points, which again is pretty tough, and I understand that it's not going to be an exact science. You don't have to be like, you know, machine precision on this or anything. But I am trying to get as close as I can to all of the points that we need to go to. So I'm going to try to graph it here. This one goes down really fast, probably about there. And this one goes to about there. And again, not perfect. It's a little bit more straight arc than I would have liked, but you know, it works out. It gets it done. Although it looks a little bit more straight, but just don't use straight lines, okay? The lines have a little bit of a curve to them, kind of like parabolas do. But anyway, there's all the stuff. So we have our increasing interval. So from -infinity to -1.57. And then we have a decreasing from -1.57 to 0.41, which I kind of made it a little bit less than half. And then from 0.41 to 1.16, it goes up and then stops. And then from 0.41 to positive infinity, it is decreasing. So those are my two decreasing, and these are my two increasing. All right, so not bad. We only have, I think, one more to go, and we will be done with this. So moving on to the last problem. Hopefully you got all this, and now we're on the last one. So go ahead and copy that information down while I ready the graph. Which this one's a pretty
I got it down.
Okay, great. So let's go ahead and move over to the graph. And again, we're just looking at a few things. We're looking at the key features. And this one, you got to be careful with this one because it's got a little tiny bit over the x-axis. So if you zoom in regularly, it might look like it's just glancing or barely touching the x-axis and then changing direction. So be careful with that one. And domain is all real numbers because it's going in both directions. You know, you're always going to get an x value. So let's say if I choose x of -10, oopsie, x equals -10, which I have this green line for that. And as I pass this green line from the left to the right, all right, I have to go a little bit down here to see where it crosses. But trust me, it's going to cross somewhere. Goes this way, and there are no holes, no gaps or anything. So I always have an x value. Y value, also all real numbers. We don't have a cap because if I move this blue line up and down, we're not missing anything. So domain and range is all real numbers. Relative maximum is this number, which again, I rounded it off to 2 decimal places instead of 3, just because in my previous classes, I didn't have enough space and I ended up having some things that were off the screen. So I just shortened it to 2 decimal places because on some of these you have to type in a lot of things, especially on the intervals. So there we go. Those are the relative maximums and minimums. And behavior. So as we go to the positive numbers, our line goes up. And as we go to the negative numbers, our line goes down. So as x goes to infinity, the function or the y value goes to positive infinity. As we go to the left to negative infinity, x, y goes to also negative infinity. So there we go. We got all the stuff we need from our graph, and we just need to go ahead and get our increasing and decreasing intervals. So I'm going to go ahead and try this one. And again, it goes a little bit above it, just like ever so much. And I can use these numbers to graph it too, but I'm just trying to get it as close as I can. So let's try to draw our graph as close as we can. Hey, that's not bad. That's probably the best one I did all day. So there you go. We have 2 increasing intervals. All right, and that's just about the end of the class, actually. Barely made it. Actually, you know what? I'm gonna. Anyway, there we go. So that's the last of them. Make sure you got all this down, and again, get your graph as close as you can. And I'm going to be a little bit easy on grading it when graphing it. So, but just make sure you have your key points. Any kind of zeros or x-intercepts, y-intercepts, your turning points, right? Those are the things I'm really looking for. But if you're using Desmos, then it should be no problem. You should be able to get to them. You should be able to get to them pretty easily. Just click on the dot and it'll give you what you need. Anyway, that is it for today. As you can probably tell, I'm feeling a lot better. I've regained most of my functions, so I think I'm going to go back to using video. I don't know, maybe I will. I don't know. It was good kind of being hidden a little bit, but it's good to be back, I guess. Anyway, that is it. Hope you enjoyed today's lesson. And I will see you next time. Bye.
Bye.